Welcome to Starry Cosmos. Welcome to Starry Cosmos. The universe has a hard limit on what we can ever see, not because of technology, but because of light itself. But what is happening just one light second past the edge of the known cosmos? Dim your lights, settle in, get comfortable, and let us begin. If these quiet journeys help you drift off, hit that like button and subscribe to Starry Cosmos, so that the next journey through the vast expanse finds you when you need it. Dim your lights, settle in, get comfortable, and let us begin. If these quiet journeys help you drift off, hit that like button and subscribe to Starry Cosmos, so that the next journey through the vast expanse finds you when you need it. The universe unfolds with a persistent and subtle grace, a quiet insistence on its own vastness. Consider for a moment the nature of light, that fundamental messenger carrying information from distant realms across unimaginable distances. We perceive it as a stream, a relentless flow of photons reaching our eyes, yet its journey is constrained by one immutable law. It travels at a finite speed, approximately 299,792 kilometers per second. And this seemingly simple fact carries profound implications for how we understand the cosmos, and indeed, the very limits of what we can see. As you turn your attention further into space, towards regions receding from us with tremendous velocity, you are not simply observing objects as they exist now, but rather peering backward in time. The light you receive has been traveling for so long, years, decades, millennia, that it is carrying the echoes of events that occurred eons ago. Each photon carries a snapshot of the universe as it was when that particular light began its journey, and the deeper you look, the further back into the past you are seeing. It is like looking through a window that simultaneously shows and reflects the history of everything beyond its surface. The implications ripple outward, shaping our understanding of distance and scale. The immense distances involved in astronomical observation create a remarkable distortion. What we perceive as distance is not simply a measure of spatial separation, but also a measure of time. A galaxy 100 million light-years away has emitted its light for 100 million years, an immense period of cosmic history, though still only a small fraction of the age of our Earth and the universe. This temporal distortion is inherent to our perspective, and it fundamentally alters how we conceptualize the vastness surrounding us. It is a humbling realization. What appears as an immense gulf of space may be quite a modest expanse in the context of time. Now, let us turn our gaze towards that spherical boundary, the edge of what we can currently observe. This is not an edge in the literal sense, like a cliff dropping off into nothingness. Rather, it represents a limit imposed by the speed of light and the age of the universe. It defines the observable universe, this sphere centered on Earth from which light has had sufficient time to reach us since the Big Bang. The calculations are complex, intertwined with our understanding of the expansion rate of space itself. But the result is astonishing. The diameter of the observable universe is estimated to be approximately 93 billion light-years. That's a truly staggering number, one that attempts to grasp the scale feels almost impossible. Imagine holding out your arm. That is perhaps a useful analogy for the vastness of our own galaxy, the Milky Way. Now picture extending both arms, stretching them out as far as you can, and then multiply that distance by approximately 93 billion times. You begin to get a sense of the sheer magnitude we are dealing with. Consider this carefully. Every point on that sphere, every galaxy, star cluster, nebula, and individual star visible to us, is sending light towards us now, light that began its journey at vastly different points in the universe's history. The photons from the most distant galaxies have been traveling for over 13 billion years, originating shortly after the dawn of the cosmos. The faint glow we detect from these ancient sources is a testament to their remarkable endurance, carrying with them information about conditions that existed in the infant cosmos. It is like listening to echoes of creation, piecing together an image of what transpired during the first moments after the Big Bang. However, it is crucial to acknowledge that this observable boundary is not a definitive wall. It is not as though there is not anything beyond. Rather, it simply means that we cannot detect it with our current tools and technologies. The light from objects located outside of this sphere has not had enough time to reach us yet. The expansion of space continues relentlessly, carrying those distant regions further and further away with each passing moment. As a result, their light is effectively receding from us at an accelerating rate. For some galaxies, the speed they are moving away is even greater than the speed of light, a consequence of the expanding fabric of space itself. Thinking about this distance often requires letting go of intuitive notions of scale and spatial relationships. The concept of beyond becomes difficult to grasp because our senses are fundamentally limited by the finite speed of light. We can only ever observe what has had a chance to reach us, creating a kind of cosmic looking glass that reflects a limited portion of reality. The vastness beyond this looking glass remains shrouded in mystery, a realm accessible only through theoretical models and sophisticated calculations based on the laws of physics. Scientists use techniques like gravitational lensing, the bending of light around massive objects, to infer the presence of galaxies located behind these intervening celestial bodies. It is like using a distorted lens to glimpse what lies beyond, providing indirect evidence for structures that remain invisible to direct observation. These observations suggest that the observable universe is likely just one small island in an even vaster ocean, a multiverse potentially teeming with countless other regions of spacetime and distinct universes. The event horizon of sight, therefore, is not a physical barrier, but rather a fundamental constraint imposed by the very nature of reality. It defines the limits of our perception, shaping our understanding of cosmic distances and forcing us to confront the profound implications of an expanding universe. As we continue to develop more powerful telescopes and observational techniques, pushing the boundaries of what is detectable, we may eventually glimpse further into this obscured realm, uncovering new insights into the structure and evolution of the cosmos. Yet for now, we remain limited by the relentless speed of light, forever looking back in time as we strive to understand the profound mystery of where everything began, and perhaps where it will ultimately end. It is a humbling acknowledgement of our place within this magnificent, ever-expanding universe, a reminder that even the most advanced instruments can only reveal a fraction of the truth. The search for understanding continues, driven by curiosity and an unwavering commitment to unraveling the secrets held within the silent expanse of space. The boundaries of our sight are not defined by technology, but by the cosmic speed limit itself. Imagine for a moment extending your gaze far beyond the familiar constellations, pushing past the shimmering spirals of distant galaxies, and then further still, into a region of space where even the most powerful telescopes cannot quite penetrate. We've defined what we can see as the observable universe, that sphere of space from which light has had time to reach us since the beginning of everything. But what lies beyond? What existed before our current view of reality, and how does it shape the cosmos we know today? The answer in many ways is held frozen within a faint, pervasive glow, the cosmic microwave background, or CMB as scientists call it. It is not a light that shines directly upon us. Rather, it is the echo of an event so ancient, so profound, that its remnants are still detectable today, a subtle whisper across unimaginable distances. Consider this. 380,000 years after the Big Bang, our universe was dramatically different from what we perceive now. It had not yet cooled enough for stars to ignite, galaxies to coalesce, or planets to form. Instead, it was an incredibly hot, dense plasma, a swirling soup of protons, neutrons, and electrons, bathed in intense radiation. Photons, the particles that carry light, were constantly bouncing off one another, creating a chaotic, opaque fog. Imagine trying to see through a thick cloud of static. That is essentially what it was like back then. But as the universe expanded, it also cooled, a process driven by the relentless push outwards from the initial explosion, an expansion we now call inflation. As the temperature dropped, electrons and protons began to combine, forming neutral hydrogen atoms. This marked a critical transition, a moment of profound consequence. With fewer free electrons to scatter them, photons could finally stream freely through space, no longer constantly bumping into matter. This recombination event released a flood of light, a light so faint that even today it is incredibly difficult to detect. This ancient light is what we now know as the cosmic microwave background, a diffuse glow spread across every point in our observable universe. It is not a single, bright source. It is more like a subtle blanket of radiation, a constant reminder of the very beginning. You can think of it as a literal wall of ancient fire, a boundary that blocks our direct optical sight to what came before, shielding us from the light of the earliest moments. It is not a barrier in the sense that you cannot pass through it. It simply acts as an impenetrable visual filter, a fundamental limit to our observational capabilities. But the CMB is not just a uniform glow. Within its faintness exist incredibly subtle temperature fluctuations, variations in density that are akin to tiny ripples frozen in time. And these are not random jitters. Scientists suspect they represent the seeds of all future cosmic structures, galaxies, clusters of galaxies, and even the large-scale distribution of matter we observe today. These minute differences in temperature arose during the inflationary period shortly after the Big Bang. Imagine areas where gravity had slightly stronger pull. Those areas expanded a tiny bit faster than others, leading to slightly denser regions that became the gravitational wells that eventually collapsed to form galaxies. The CMB is therefore a treasure map of the infant universe, encoded in its temperature variations. By painstakingly mapping these fluctuations, a monumental undertaking involving space observatories like Planck and WMAP, we are essentially reconstructing the earliest stages of cosmic evolution. The patterns we observe within the CMB tell us about the geometry of space itself, whether it is flat, curved, or something else entirely, a question that has occupied cosmologists for decades. The data strongly suggests our universe is remarkably close to being flat, an astonishingly precise result given the immense distances involved and the sensitivity required to measure these faint temperature variations. It is crucial to understand this is not like looking at a photograph of something happening now. It is observing something that happened over 13.8 billion years ago, when the universe was but a fraction of its current age. The light we are seeing has traveled for nearly the entire history of the cosmos to reach our telescopes, carrying with it information about the conditions in the early universe, conditions vastly different from those we experience today. This makes interpreting the CMB incredibly challenging, requiring sophisticated theoretical models and painstaking analysis. But the rewards, a deeper understanding of how our universe began and evolved, are immense. The study of the CMB is not just limited to mapping temperature variations. Scientists also look for polarized light within the background, a subtle twisting of the photon's direction of travel. This polarization provides further clues about the early universe, revealing details about the magnetic fields that existed at the time and offering insights into the physics of inflation itself. The detection of primordial B-mode polarization, a specific pattern in the CMB's polarization caused by gravitational waves from the inflationary epoch, would be a monumental discovery, providing direct evidence for the theory of cosmic inflation and opening up new avenues for exploring fundamental physics. Consider the sheer scale of this endeavor. The CMB is observable from virtually every direction in our sky, yet its temperature variations are incredibly faint, just a few parts per million warmer or cooler than the average background radiation. Detecting these minuscule differences requires instruments with unparalleled sensitivity, located far away from sources of interference on Earth. Dedicated microwave instruments, for example, are specifically designed to observe the CMB with exceptional precision, pushing our understanding of the early universe to new frontiers. As we continue to refine our observations and develop more sophisticated analytical techniques, we can expect to uncover even deeper secrets hidden within this ancient echo. The CMB is not merely a relic. It is an active area of research, constantly yielding new insights into the nature of space, time, and matter. It is through studying these subtle variations that we begin to unravel the mysteries of the universe's origins, to understand not just what happened in the past, but also how our universe evolved into what it is today. And as you settle deeper into this quiet contemplation of the cosmos, remember, every flicker of light, every faint gradient within the CMB represents a step closer to comprehending the grand narrative of everything that ever was, and perhaps even hinting at what might be yet to come. It is a humbling reminder of our place within the vastness of existence, a connection forged through the shared echoes of the Big Bang, an echo that whispers across billions of years and continues to shape our understanding of the universe we inhabit. Every direction we look in the night sky terminates in this ancient wall of primordial fire. The fabric of existence stretches onward, an immense tapestry woven from space-time itself, and as you gaze into its depths, a profound question emerges. What lies beyond? We've charted vast distances across our own observable universe, mapping galaxies clustered like islands in an endless sea. Yet the edge we perceive, the boundary that defines our view, is not fixed. It shifts, it recedes, driven by a force we barely comprehend, dark energy. Consider for a moment the slow, deliberate dance of gravity, pulling everything towards each other with a relentless insistence. For billions of years, this was the dominant narrative, a predictable progression of celestial bodies drawn together in spirals and mergers, governed by the ancient rule of attraction. Then, about 5 billion years ago, something unexpected began to occur, an alteration in the cosmic choreography that has fundamentally reshaped our understanding of reality. It started with subtle anomalies, tiny deviations in the light from distant exploding stars, known as Type Ia supernova. These slight shifts in wavelength, meticulously measured over decades by dedicated telescopes, suggested a disturbing possibility. The universe was not simply expanding, it was accelerating its expansion. Initially, scientists were baffled, struggling to reconcile this observation with everything they understood about physics. Einstein's theory of general relativity predicted that gravity should be slowing down the expansion initiated by the Big Bang. But the data pointed relentlessly toward an opposing force, something pervasive and enigmatic acting on a scale far grander than anything previously imagined. This unseen agency became known as dark energy. Dark energy represents roughly 68% of the total energy content of the universe, yet its nature remains one of the most significant unsolved mysteries in science. We know it is there because we observe its effects, this accelerating expansion, but what is it? The leading hypothesis suggests that dark energy is a property of space itself, an intrinsic tension inherent in the very geometry of space-time. As the universe expands, more and more space is created, thereby generating more dark energy, which then fuels further expansion. Think of it like inflating a balloon. As you inflate it, the surface area increases proportionally to the cube of the radius, meaning that the volume increases much faster than the surface does. Similarly, with eternal inflation driven by dark energy, space itself is constantly growing at an ever-increasing rate. Now, let us contemplate what this expansion means for distant galaxies, those shimmering pinpricks of light located billions of light years away, distances so vast that their light has taken eons to reach us. As the universe expands, these galaxies are not merely moving away from us, they are receding at an ever-increasing speed. If you were to calculate their velocity using Hubble's law, a simple relationship between distance and recessional speed, you would find it increasing over time. This is not due to their own motion through space, but rather the expansion of space-time itself carrying them along with it. The more distant a galaxy is, the faster it appears to be moving away from us, until eventually they approach the cosmic event horizon. The cosmic event horizon is essentially an invisible boundary, a point beyond which we can no longer observe anything, not light, not radio waves. Nothing from that object will ever reach our eyes. It is the furthest distance any observer, anywhere in the universe, can see from a given distant galaxy. For galaxies relatively close to us, perhaps within a few billion light years, the event horizon is still far enough away that we continue to receive their faint glow. But for galaxies located at the very edge of our observable universe, those currently receding faster than the speed of light, they are steadily approaching this boundary. And here's where the true scale of the situation becomes apparent. Every second, stars within these rapidly receding galaxies are being carried beyond that event horizon, lost to our view forever. It is not a violent or dramatic process. It is an inevitable consequence of the accelerating expansion. These stars, the remnants of long-dead suns and their planetary systems, are simply swept out of existence, becoming irrevocably part of the dark universe, a region beyond our ability to see, measure, or understand. Consider this. Within your own lifetime, countless stars will have crossed this invisible barrier, silently disappearing from our cosmic neighborhood never to return. The implications are profound. It suggests that our observable universe is not static. It is shrinking in the sense that we are constantly losing access to a portion of its contents. The further we look into space, the smaller the part of the universe we can see, as if peering through an ever-tightening window. This is not a catastrophic cosmic implosion. It is simply the natural consequence of an expanding space-time dominated by dark energy. It is a humbling reminder of our limitations, of the vastness that lies beyond our perception and comprehension. Scientists suspect that this accelerating expansion is directly linked to a mysterious energy field permeating all of space, a theorized quantum vacuum fluctuation generating the force driving it. They are exploring various models involving fields like quintessence or modifications to general relativity to fully explain its origin, but definitive answers remain elusive. The James Webb Space Telescope, with its unparalleled infrared capabilities, is providing increasingly detailed observations of distant galaxies, allowing astronomers to refine their understanding of this expansion and to probe deeper into the mysteries surrounding dark energy. The telescope is not just capturing images, it is measuring redshift, a shift in the wavelength of light caused by the Doppler effect as an object moves away from us. Larger redshifts indicate greater distances and faster recessional speeds, offering crucial data points in our ongoing quest to unravel this cosmic enigma. Furthermore, observations from supernova remnants offer another valuable avenue for investigation. By studying the brightness and redshift of these exploding stars, the most powerful events in the universe, scientists can constrain the nature of dark energy and test different cosmological models. Each observation, each measurement, brings us closer to a more complete picture, yet the fundamental questions remain stubbornly persistent. It is like tracing ripples on a pond. We can see the initial disturbance, but understanding the source of the disruption, the stone that created the waves, requires far greater complexity. The concept of the receding horizon and dark energy offers an increasingly stark portrayal of our place within the grand scheme of things. It reminds us that there is always more beyond what we presently perceive, a vast realm shrouded in darkness, a region growing larger with every passing second, carrying away with it the light and stories of countless vanished stars. As you continue to contemplate these concepts, remember that scientific understanding is not about providing definitive answers, but rather about persistently refining our questions, pushing the boundaries of what we know, and embracing the inherent wonder of the unknown. Let the sheer scale of this unfolding universe sink in through your senses, the distances involved, the timescales stretching across billions of years, and allow yourself to simply be in its presence. The universe is slowly closing its windows, locking away stars in the unobservable dark. If you were standing at a window, peering out into the night, and suddenly granted the capability to teleport, a direct, instantaneous shift of location to just beyond the edge of what we can see, the familiar comfort of your surroundings would remain. The lawn beneath your feet, the distant rooftops shimmering in the twilight, the subtle glow of street lights, all would be exactly as you remember them. The vastness of space would not immediately assault your senses with a sense of utter unfamiliarity, but rather, you would find yourself nestled within an astonishingly ordinary-looking expanse. It is a profound notion, is not it? That the boundary we perceive, the limit of our observation, does not necessarily denote a dramatic discontinuity, a sudden transition into something wholly alien and incomprehensible. Instead, consider this. Even at the furthest reaches of what we can detect, space itself continues, uninterrupted, like a seamless fabric stretching out indefinitely. And that is 1 light second away from here. Now, let us contemplate just how incredibly distant 1 light second truly represents. A light second is simply the distance light travels in 1 second, approximately 299,792,458 meters per second. This is not a measurement of time. It is a measure of spatial extent. It is a mind-bending scale to grasp, but profoundly important for our understanding of these immense distances. 1 light second at the edge of the observable universe is roughly 63 trillion kilometers, or nearly 4 billion times the distance between Earth and the Sun. To put it into perspective, you could travel at the speed of light for nearly 6 years continuously to reach that boundary. Yet you would still be moving through space that remains fundamentally similar to the space you have traversed before. It is a disconcerting possibility, is not it, to think of such unimaginable distances existing alongside what feels so intimately familiar. Just 1 light second past this horizon, beyond the veil of observation, lies a realm of completely unseen galaxies and systems. Galaxies that have formed since the very beginning of the universe, galaxies that will continue to form long after our own sun has exhausted its fuel. Galaxies that are fundamentally different from everything we have ever studied or imagined. They are not simply dark because they are absent. They are dark precisely because they are inaccessible to us. Their light, the very essence of their existence, has never had a chance to reach our telescopes. They exist in a state of perpetual isolation, shrouded behind an impenetrable curtain of space and time. Scientists suspect that many of these galaxies are vast, irregular collections of stars and gas, far more massive than even our own Milky Way. Some may be swirling giants, dominated by supermassive black holes at their centers. Others might be relatively small, dense clusters of stars huddled together in gravitational harmony. And countless more, perhaps vastly different from anything we can currently conceive, are hidden within this unobservable expanse. The nature of these unseen galaxies is a source of ongoing speculation and research. We rely heavily on simulations and theoretical models to extrapolate what they might be like, based on our understanding of galaxy formation and evolution. Cosmological simulations, using supercomputers to model the interactions of dark matter and gas in the early universe, suggest that the distribution of galaxies is not uniform. Instead, they are arranged in a complex interconnected network, a cosmic web, with colossal filaments stretching across billions of light years, threaded by vast voids. These filaments represent regions where galaxies tend to cluster together, influenced by gravity and the underlying structure of dark matter. The unobservable galaxies we hypothesize exist primarily within these dense regions, hidden from our direct view, but inextricably linked to the visible universe around us through gravitational interactions. And here's a remarkable point that emerges from modern physics. The prevailing theory, rooted in Einstein's theory of general relativity, suggests that space is not merely an empty void. It is a dynamic, interwoven fabric, influenced by mass and energy. This fabric is not rigid or fixed. It can be curved, warped, and stretched. And the astonishing conclusion is this: modern physics indicates that space continues smoothly and continuously across the boundary of the observable universe. The edge is not an abrupt cliff or a solid barrier. It is more akin to a horizon at sea, where the water appears to vanish into nothingness, though it still extends outwards indefinitely. At 1 light-second away, there is no fundamental change in the geometry of space, no sudden shift to a different kind of thing. It is simply a region where our ability to observe, to detect light and other forms of electromagnetic radiation, is prevented by the distance involved. Think about it in terms of perspective. Imagine standing on a vast, flat plain, extending infinitely in all directions. You can see only a small portion of that plane at any given time, due to the limitations of your vision and the curvature of the Earth. However, the rest of the plane continues onward, remaining fundamentally unchanged. The same principle applies to the observable universe. We are simply viewing a limited segment of an infinitely extended space. The light from distant galaxies has not ceased to travel. It is simply taking so long to reach us that it appears as though they no longer exist. Measuring the redshift of these galaxies, the stretching of their light waves due to the expansion of the universe, provides strong evidence for this continuous nature of space-time. Redshift is not a physical alteration of the galaxy itself, but rather a consequence of the expanding space between us and the galaxy causing its light to stretch, much like the sound of an ambulance siren getting lower in pitch as it moves away from you. The concept of a smooth, continuous universe is profoundly liberating. It removes the likelihood of bizarre topological features, like wormholes or naked singularities, that were sometimes considered possibilities within early cosmological models. It reinforces the idea that our fundamental physical laws are consistent throughout this immense expanse. Although we hypothesize about and investigate dark matter and dark energy to better understand the expansion driving this observable horizon, the underlying fabric of space remains fundamentally as Einstein predicted, and continues, without interruption, past the boundary we can perceive. The universe does not end at a point. It simply becomes increasingly difficult to observe. The farther out one goes, the more subtle, faint, and redshifted the light becomes, until eventually it fades entirely beyond our reach. Consider, too, that this continuous extension implies an enormous number of possibilities, the potential for countless new discoveries awaiting us, should future generations develop the technology to probe these distant realms. Perhaps we will find galaxies with exotic chemical compositions, harboring life forms unlike any we have ever encountered. Perhaps we will uncover entirely new physical laws governing the behavior of matter and energy in environments radically different from our own. The universe is not a static picture. It is an ongoing story, a vast, unfolding drama played out across billions of years. And even though one light second represents an almost unimaginable distance, within that space, everything continues: the dance of galaxies, the interplay of gravity, and the relentless march of time. It is a reminder, ultimately, of how much remains unknown about our place in this grand cosmic narrative, and of the endless potential for exploration and understanding. What lies one light second past the edge of our vision is simply more universe, waiting in the dark, and today we are venturing further still, attempting to grasp what might exist beyond that very edge, not just physically, but conceptually. We will be considering the notion of eternal cosmic inflation, a theory proposed in the late 1980s by Alan Guth, and later developed by many brilliant minds. It is a difficult idea to truly encompass, because it fundamentally alters our understanding of space and time themselves, suggesting that the universe we perceive is not just expanding, but is constantly, inexhaustibly expanding, and at speeds exceeding anything we can readily imagine. Consider this: the expansion of our observable universe, the portion from which light has had sufficient time to reach us, is itself accelerating due to what we call dark energy. But Guth's theory goes a step beyond that simple acceleration, proposing that inflation is not just something that happened at the beginning of the universe. It is an ongoing process, a fundamental property of space-time itself. He suggested that immediately after the Big Bang, and this is key, space did not simply expand from a single point. Instead, it underwent a period of incredibly rapid expansion, stretching out to an unfathomable size in an unbelievably short amount of time. And crucially, he proposed that this was not just a one-time event. Rather, the inflationary process continues to happen now, constantly creating new regions of space that are receding from us at speeds faster than light. Think about it not as expanding into something else, but as expansion of itself. Like ripples spreading outward across a pond after you drop a stone, these pockets of inflating spacetime are continuously being born, each one moving away from the last with ever-increasing velocity. Now, the physics governing this inflation are not fully understood. We can describe the theory mathematically and observe its effects through observations like the cosmic microwave background, but it leads to some truly staggering conclusions. Because if space is expanding at these phenomenal speeds, there are regions out there that are already so far away from us that their light will never reach us. They are effectively beyond our observable horizon. And within those extremely distant regions, inflation is not just continuing, it is intensifying. This intensification gives rise to the concept of bubble universes. Imagine a loaf of raisin bread rising in the oven. Each bubble represents a pocket universe, inflating independently from the others. As each bubble expands, it forms its own separate space-time, creating its own set of conditions, its own laws of physics. The expansion within each bubble continues indefinitely, driven by inflation. Now, our own universe is just one such bubble within this larger, eternally inflating multiverse. And the astonishing thing is that these other bubbles are not necessarily similar to ours. They might have different values for fundamental constants, different masses for elementary particles, different strengths of gravity, even entirely different numbers of spatial dimensions. It is a truly humbling idea that the universe you inhabit, with all its familiar laws and conditions, is not unique or special at all. It is just one possibility among an infinite number of others, each existing in its own isolated realm, expanding outwards from its own Big Bang. The mathematics suggests that there is no limit to the number of these bubble universes, an effectively infinite multiverse constantly being born and expanding. Consider also that some theories suggest that the fluctuations within inflation itself could lead to variations within each bubble universe, leading to a truly staggering diversity. And as these bubble universes continue to inflate, they can collide with one another. These collisions would be cataclysmic events on a scale almost impossible to comprehend, releasing enormous amounts of energy and potentially disrupting or even destroying the existing bubble structures. We do not have any direct observational evidence of such collisions, obviously, but their possibility is theoretically sound within this framework. The idea that our own universe might have originated from a collision with another bubble universe, a cosmic egg event, has been proposed, although it remains highly speculative. Furthermore, the very concept of distance becomes profoundly complicated in an eternally inflating multiverse. Because space itself is constantly expanding, the distances between these bubbles are also increasing at an accelerating rate, and they are never truly ending. There's no central point or boundary to this vast expanse. It simply stretches on forever, filled with an infinite number of burgeoning universes. This is not just about locations in space. It is about fundamentally altering our perception of time and reality. The leading idea is that the inflationary period was not a fleeting moment in history, but a continuous, ongoing process. It does not require a single initial bang to set everything off. It is inherent to the nature of spacetime itself. Think of it like a perpetual engine, constantly generating new activity and expanding the possibilities. The mathematics associated with this model is complex, drawing heavily on concepts from string theory and quantum field theory, and continues to be refined as we gather more observational data about the early universe. However, let us return for a moment to the core idea of scale. While our observable universe has a finite size, limited by the distance light could have traveled since the Big Bang, the inflating multiverse is truly without limit. It is not simply larger. It is fundamentally larger than anything we can conceive, extending infinitely in all directions, containing an infinite number of other universes, each potentially governed by different rules and possessing their own histories and possibilities. The sheer scale of this concept is difficult to grasp, almost beyond our capacity for human intuition. The fact that inflation continues indefinitely, spawning a multiverse of diverse bubble universes, changes our perspective on the very nature of reality. It suggests that the laws we observe are not necessarily universal. They are simply local conditions within a particular bubble universe. And it raises profound questions about our own existence. Why do we find ourselves in this particular universe, with these specific physical constants? Is there any reason to expect that this combination of circumstances is anything other than utterly random? And if so, what does that ultimately tell us about the nature of existence itself? Certainly, it is a profound and unsettling thought when considering our place within the grand scheme of things. While we continue to explore the universe with ever-increasing precision, unraveling its secrets one observation at a time, we are simultaneously confronted with the possibility, and perhaps probability, of an infinite multiverse stretching out beyond our comprehension, filled with universes vastly different from our own. The pursuit of understanding these concepts does not necessarily offer definitive answers, but it does enrich our vision and deepen our appreciation for the unimaginable vastness and complexity of reality. A complexity that seems to extend far beyond the confines of our own observable universe, and into realms we can only begin to contemplate. The ongoing investigation continues, propelled by theoretical models and increasingly refined observational data, a testament to humanity's enduring curiosity about the deepest mysteries of existence. Our entire observable space is but a single drop in an infinite ocean of bubble universes. If you find yourself drawn to the quiet expanse of space, let us consider a structure far larger than any single galaxy, a scaffolding upon which all galaxies are built, the cosmic web. It is not simply a collection of galaxies clustered together. It is an immense, interwoven network, a skeletal framework spanning unimaginable distances, connecting every galaxy cluster within our observable universe. Imagine, if you will, a colossal sponge, its pores filled not with water but with dark matter and hydrogen gas. That's a basic analogy, but one that captures the essence of this fundamental architecture of existence. These filaments are not visible to us directly. We cannot see the substance flowing through them, only their gravitational effects. Yet they are there, shaping the distribution of galaxies in a way that fundamentally alters our understanding of how the universe evolved. Scientists suspect their formation began even shortly after the Big Bang, as primordial density fluctuations amplified over time, slowly coalescing into these ever-expanding strands. The very nature of dark matter plays an essential role here. Because it interacts only through gravity, it does not emit or reflect light. Consequently, we cannot directly observe it. However, its gravitational influence is unmistakable, acting like a subtle hand guiding the flow of galaxies and shaping the structure of the cosmic web. These filaments are not static. They are dynamic, constantly growing and evolving as dark matter continues to collapse under gravity. They shift and twist, bending space itself around them, a testament to the immense power governing this grand design. Within these luminous strands, you will find clusters of galaxies, each containing hundreds or even thousands of individual galaxies, bound together by their mutual gravitational attraction. But the filaments themselves are far more extensive, extending for billions of light years, dwarfing the distances between even the most distant galaxy groups within our observable horizon. Now let us consider how gravity operates on this scale. Every galaxy is not merely floating in space. It is caught in a flowing current, guided along these filaments toward massive gravitational attractors, colossal clusters and superclusters of galaxies. Think about a river winding through the landscape. The water follows the contours of the terrain, gradually converging towards a larger stream or even a vast ocean. Galaxies behave similarly, inexorably drawn into the deeper currents of the cosmic web. Locally, within your own galaxy, The Milky Way, for example, you experience gravity as the force that keeps you tethered to this planet and pulls it around the sun. However, on scales far greater than our solar system, galaxies are subject to a more complex dance of gravitational forces, where they are essentially passengers caught in a larger, ongoing flow. The forces at play here are extraordinarily subtle and gradual over the immense timescales involved. It is not a sudden tug or push, but a persistent, gentle drag, a suggestion of direction rather than an absolute command. The further you travel along a filament, the stronger this pull becomes, until you reach a gravitational attractor such as a galaxy cluster, a behemoth containing millions of galaxies bound together by their common gravity. Once within its embrace, you are effectively trapped, drifting along with the flow until you either collide with another galaxy or eventually pass beyond the limits of the cluster itself and continue down a different filament. These attractors, colossal concentrations of mass, become nodes in the cosmic web, points where streams of galaxies converge and exchange momentum. And here's where it gets truly remarkable. These filaments do not stop at the horizon. The observable universe is defined as the portion of space from which light has had enough time to reach us since the Big Bang. But the cosmic web extends far beyond that boundary, stretching infinitely into the unobservable deep, a realm inaccessible to our current instruments and understanding. It is like imagining a vast ocean. We can only see a limited section of it at any given time, but there is an infinite expanse behind the horizon. Similarly, the filaments continue even after the light from them has been cut off by the expansion of space and no longer reaches us directly. They exist as echoes in the gravitational field, influencing the distribution of galaxies we do see, a subtle reminder of their immense scale and interconnectedness. Scientists use sophisticated computer simulations to model the growth and evolution of these structures, feeding them with data from telescopes like Hubble and James Webb. These models predict that filaments extend far beyond what we can currently observe, creating a vast, unseen network connecting galaxies across immeasurable distances. The distribution of matter within these filaments is not uniform. Dense regions, called nodes, appear sporadically along their length, occasionally harboring galaxy clusters or even superclusters. These nodes could be the seeds for future structures, as dark matter continues to collapse and new galaxies form. The concept of Laniakea, the region where our Milky Way resides, is particularly relevant here. Laniakea is not simply a local neighborhood. It is part of a much larger structure known as the Great Attractor, a gravitational anomaly pulling on everything within its reach. This attractor itself is thought to be connected to other similar attractors via filaments stretching across vast spans of space. Our own galaxy's movement through Laniakea reveals that we are not isolated. We are part of an immense flow, guided along one of these filaments towards a massive attractor, and ultimately toward the wider cosmic web. Understanding this flow is key to unraveling the history of our local neighborhood and its place in the grand scheme. The study of gravitational flows within the cosmic web helps us understand how galaxies formed and evolved over billions of years. The density fluctuations in the early universe, tiny variations in the distribution of matter, seeded the formation of dark matter halos, which then attracted ordinary gas and eventually ignited star formation within them. Galaxies formed at the nodes of these filaments, fueled by the abundant supply of gas drawn along the streams. As galaxies collided and merged over time, they further shaped the structure of the cosmic web, adding to its complexity and richness. Examining these flows also provides insights into the distribution of dark matter, which is thought to be more concentrated within the filaments than in the voids between them, a key observation supporting our current cosmological models. Furthermore, research increasingly suggests that the pathways within these filaments are not simply linear strings. They are actually complex, three-dimensional networks, riddled with twists and turns dictated by the underlying distribution of dark matter. These intricate structures influence the motion of galaxies in ways that are difficult to predict, but fundamentally shape the large-scale structure of the universe. The exact nature of these pathways, whether they are dominated by cold or hot dark matter, remains a subject of ongoing investigation and provides a rich area for future astronomical research. As we develop more powerful telescopes and refine our theoretical models, we can expect to gain an even deeper understanding of this remarkable cosmic architecture, a vast web woven throughout the universe, connecting all things in an eternal flow. The filaments represent not just connections between galaxies, but the very fabric of space itself, subtly sculpted by gravity over billions of years, extending far beyond the limits of our direct perception, and hinting at the profound interconnectedness of everything within existence. The cosmic web stretches on, a continuous loom weaving matter across the boundaries of sight. If you have contemplated the immensity of space, if you have found yourself gazing at a dark sky filled with ancient light, then perhaps you will find this journey resonant. We are now considering a realm far beyond the visual reach, where the very fabric of reality seems to bend and twist in ways that challenge our conventional understanding, a place where the peculiar behavior of quantum mechanics might offer a bridge between what we see and what, fundamentally, remains hidden. We are looking at the possibility, a remarkably speculative yet deeply intriguing one, of quantum entanglement extending beyond the boundary defined by our observable universe. Let us explore this idea through the lens of the event horizon and its implications for the connectedness of all things. Quantum mechanics, as you know, operates under a set of rules profoundly different from those governing our everyday experience. It dictates that particles are not simply little billiard balls traveling in straight lines. Instead, they exist in states of probability until measured, at which point they seemingly collapse into definite locations and momenta. One of the most baffling aspects, and simultaneously most profound, of this theory is quantum entanglement. Entanglement describes a bizarre correlation between two or more particles, where their fates are inextricably linked regardless of the distance separating them. Imagine two coins flipped simultaneously. Classically, each would land randomly on heads or tails. But if they are entangled, knowing the outcome of one instantly reveals the outcome of the other, even if those coins are light years apart. This is not a matter of information traveling faster than light. It is a deeper connection woven into the fundamental nature of reality. It is as though they share an unseen thread, a ghostly link that persists despite spatial separation. Now consider an event horizon, the boundary around a black hole from which nothing, not even light, can escape. This is not merely a point in space. It is a region defined by extreme gravity, a place where space-time itself is warped beyond recognition. As you approach an event horizon, time slows down relative to an external observer, and all paths lead inevitably inward. From our perspective outside the black hole, we see objects falling toward its center, their images increasingly redshifted and fading until they disappear completely. But what if this seemingly absolute boundary, this point of no return, does not truly mark the end of connection? What if, as particles venture across this horizon, remnants of their entangled partners remain within our observable universe, still subtly linked to those that have journeyed beyond? The concept is rooted in theoretical physics and relies on extrapolating established quantum principles into extreme gravitational environments. Scientists suspect that while information cannot travel faster than light through space-time, a cornerstone of Einstein's theory of special relativity, it might be able to travel around the event horizon via entanglement, effectively bypassing the limitations of conventional communication. This is not truly traveling in the sense of moving through space. Rather, it is a leveraging of this intrinsic connection between entangled particles. The mathematics surrounding this possibility are complex and still under active investigation, involving ideas like wormholes or connections mediated by the geometry of space-time itself, concepts that push us to the very edges of our current understanding. Think about it in terms of cause and effect. An event occurring on one side of an entangled pair instantly influences the state of its partner, no matter how far apart they are. Now imagine a particle falling toward a black hole's horizon. Its entanglement with its counterpart, perhaps one that has not yet crossed the boundary, would theoretically maintain this instantaneous correlation, even as the first particle is drawn inexorably into the singularity at the black hole's center. The key is not that information is being transmitted. It is that the state of both particles remains correlated, a shared quantum reality preserved across an otherwise insurmountable distance. This is not simply a philosophical exercise, though. The implications extend to our understanding of spacetime itself. If entanglement can transcend the event horizon, it suggests that our concept of a sharply defined boundary between what we see and what we do not may be fundamentally flawed. It hints at a more interconnected universe, a cosmos where regions previously considered isolated are actually linked through these subtle quantum threads. The observable universe, as we perceive it, might represent only one small facet of a vastly larger, entangled whole. Researchers have begun to model scenarios simulating this kind of entanglement across black hole horizons, using sophisticated computer simulations. These models demonstrate that the remaining correlations between particles could, in principle, be maintained and even amplified by gravitational effects altering the quantum state. The specific details depend heavily on the nature of the spacetime geometry surrounding the event horizon. However, these theoretical explorations consistently point toward a remarkable degree of persistence for entanglement across this boundary. It is important to acknowledge that we are venturing into highly speculative territory. Direct experimental confirmation is incredibly challenging, if not currently impossible, given the extreme conditions near black holes. However, ongoing advancements in quantum information theory and gravitational physics offer tantalizing avenues for theoretical investigation. Some research even explores the connection between entanglement and the holographic principle, a radical idea suggesting that our three-dimensional universe might be encoded on a two-dimensional surface located at its edge. This holographic view imagines everything within our observable space as being ultimately projected from, or inseparable from, a boundary far beyond what we can directly perceive. Consider the Voyager probes, for instance, those intrepid spacecraft venturing deeper and deeper into interstellar space. They carry with them a golden record, a message to any potential extraterrestrial civilizations, containing information about Earth and humanity. These probes are already effectively beyond our immediate observational reach, yet the fundamental quantum entanglement they share with particles within our observable universe continues to persist. This is not just a curiosity. It is a demonstration of how deeply intertwined we all are within this vast cosmos, a connection that transcends distance and defies the limitations imposed by what we can directly observe. The concept also opens up fascinating questions regarding the information paradox associated with black holes. How does information disappear when matter falls into a black hole, violating the laws of quantum mechanics? If entanglement extends beyond the horizon, It suggests that this lost information is not truly lost at all. It remains encoded in the correlations between entangled particles. It would imply a fundamentally new way to think about the process of black hole evaporation, and potentially offer insights into the ultimate fate of these enigmatic objects. Thinking about the implications is akin to contemplating an infinite tapestry, where every thread, no matter how distant or obscured, is inextricably woven with all others. The event horizon, then, is not a wall. It is merely a shift in perspective, a boundary that defines what we can observe but does not necessarily define what is. The universe is structured by intricate relationships and subtle correlations, and quantum entanglement presents one of the most compelling pieces of evidence for this interconnectedness. It reminds us that our perception of reality is fundamentally limited by our senses and instruments, and that the deepest mysteries often lie just beyond the reach of immediate observation. This exploration continues to push at the edges of knowledge, inviting us to reconsider everything we think we know about space, time, and the very nature of existence. It is a reminder that even the vast expanse of the cosmos may ultimately be held together by threads far finer than light. An invisible quantum thread binds our world to the unseen, bridging the divide of light itself. If you find yourself drawn to contemplate the vastness of existence, to consider the questions that stretch beyond human comprehension, then let us turn our gaze towards a possibility often relegated to the realm of theoretical physics, a notion that seeks to redefine our fundamental understanding of space itself. We are going to explore the idea of topological loops and curved universes, venturing into the profound quiet where geometry yields to suggestion. Consider with me, as we drift through an expanse measured in incomprehensible distances, the subtle question: is space truly infinite, or does it possess a hidden, curving structure? The prevailing cosmological model, based on decades of observation and increasingly precise measurements from missions like Hubble and Planck, paints a picture remarkably consistent, a universe that appears geometrically flat. This flatness implies an infinite expanse, stretching out eternally in every direction. It is a beautiful, elegant notion, compatible with the standard Big Bang theory, and offering a compelling framework for understanding the expansion of space itself. However, this flatness is not necessarily an absolute truth. It could be a local approximation, a characteristic of our observable region rather than a universal property. Think of it like looking at a small patch of rough fabric. It might appear flat to your hand, but zoom out far enough and you will see the underlying weave, the folds and curves that define its three-dimensional shape. Now imagine instead that this fabric of space is not just flat, but gently curved into a complex, higher-dimensional structure, something like a three-dimensional torus. A torus is simply what you get when you take a sheet of cardboard, twist it once, and glue the ends together. You've created a donut shape, though one that exists in 4 dimensions, a concept admittedly difficult to fully grasp. The universe, according to this hypothesis, would resemble a similar structure. Everywhere you look, as far as our telescopes can see, appears flat. But if you were to travel far enough along any given line, an enormous distance, beyond what we currently have the capacity to observe, you might eventually find yourself returning precisely where you started. It is not a literal loop in the traditional sense of traversing a circle on a plane, because space itself is curved. Instead, imagine a sphere. If you walk around its surface for long enough, you will inevitably return to your point of origin, even though the distances traveled are increasing. The universe, then, could be sculpted into something akin to this vast, unseen donut, with our observable region being just one finite slice within the larger structure. Scientists suspect that the geometry we observe is a consequence of its relatively small size compared to the overall curvature. Just as the surface of a large marble appears flat to a small insect crawling across it, so too does our observable universe seem flat to us, who are confined within this limited region. The sheer scale involved, billions of light years, means that the subtle curvature is effectively masked by the expansion of space itself. It is a humbling reminder of our limitations and the vastness of what lies beyond our perception. The idea of a curved, looping universe does not inherently conflict with established physics, particularly Einstein's theory of general relativity, which describes gravity as a distortion of space-time. General relativity predicts that massive objects warp the geometry around them, creating the space-time curvature we observe through gravitational lensing and the bending of light. A large enough mass, spread over a sufficiently vast area, could indeed create this toroidal structure, a universe sculpted by its own immense scale. The equations work, the mathematics is sound. However, there is no direct observational evidence yet to definitively confirm such a configuration, which makes it a subject of ongoing theoretical investigation and indirect cosmological studies. Think about the implications for our understanding of the cosmos. If space curves back upon itself, then the distances between points become non-Euclidean, meaning they are not governed by the familiar rules of straight lines and right angles. Distances would be significantly different from what we calculate based on our everyday experiences. The concept challenges our intuitive notions of location and distance, forcing us to confront the possibility that the universe operates according to a geometry far more intricate than initially assumed. And as we ponder the shape of this infinite, or perhaps finite, realm, allowing ourselves to contemplate such profound concepts, something remarkable occurs, a subtle shift in perspective. The relentless striving for precise measurements and quantifiable data seems to soften, replaced by a gentle yielding to the immense scale of things. The mind, freed from the constraints of localized observation, begins to relax into the endless silence of the void, a quiet spaciousness not defined by emptiness, but by an infinite potential. It is within that silent contemplation, that surrender to the unknown, that we can begin to grasp something of the universe's true nature. The question then is, how do we test such a radical hypothesis? While detecting direct evidence of a torus would be extraordinarily difficult, astronomers are exploring several avenues of investigation. For example, subtle anomalies in the cosmic microwave background. The afterglow of the Big Bang could potentially provide clues about the underlying geometry of space-time. The polarization patterns within this background radiation might reveal distortions indicative of curvature. Furthermore, detailed mapping of galaxy distributions, the way galaxies cluster and spread across the universe, could also offer indirect evidence supporting or refuting the toroidal model. Dark matter and dark energy play an important role in these considerations as well. Their influence on gravitational forces and expansion, impacting the overall shape of the cosmos. The distribution of these unseen components would provide further constraints on our understanding of space-time geometry. Simulations based on various cosmological models, including those incorporating curved universes, are constantly being refined and compared against observational data. Ultimately, the investigation into the curvature of space represents a fundamental quest to understand the very fabric of reality, a journey that pushes the boundaries of human knowledge and challenges our deepest assumptions about the nature of existence. It is a humbling reminder that even after centuries of scientific advancement, we are still grappling with some of the most profound mysteries of the universe. And perhaps within this exploration lies not just a deeper understanding of space itself, but also a greater appreciation for our place within it, a quiet acknowledgement of the infinite potential held within everything that exists and everything that might yet be. The endless panorama unfolds before us, light years spent traveling to reach these distant formations are now reduced to stillness as we reflect on the possibilities of an overarching structure, an unseen geometry that may shape us in ways we can only just begin to imagine. The thought invites a deeper serenity, a release from the need for absolute certainty, and a quiet acceptance of the profound mystery at the heart of it all. Perhaps the universe is a loop, an infinite cycle where the end is always the beginning. If you have ever looked up at the night sky, a sense of scale tends to descend upon you, a humbling awareness of our tiny place within an immense and ancient cosmos. And yet, for all this vastness, we often focus on what lies within it, the swirling arms of our Milky Way galaxy, the distant glimmer of other galaxies pulled into its gravitational embrace, imagining journeys toward them, always seeking connection. But let us turn now to a journey not outward, but inward, a contemplation of where even those connections ultimately lead as time unfolds, and what kind of silence awaits beyond the visible boundaries of our universe. Consider this: space is not static. It is expanding, relentlessly stretching outwards, carrying all elements within it along with its relentless advance. And this expansion is not just a happening around us. It is a fundamental property of the cosmos itself. Over unimaginable stretches of time, trillions upon trillions of years, this expansion will fundamentally reshape our universe in ways that are difficult to fully grasp, even for scientists who dedicate their lives to understanding them. You will become aware, over these immense periods, that you exist increasingly isolated within an ever-widening sphere of reality. As the universe continues its outward push, galaxies will gradually drift past what we currently perceive as our observable horizon. This is the boundary beyond which light has simply not had enough time to reach us since the Big Bang. It is a limit defined by the speed of light and the finite age of the universe, a cosmic speed limit that dictates where we can see. But the expansion is not just affecting what we can see. It is altering the very fabric of space itself, stretching distances between galaxies so dramatically that even those that were once within our observational range will eventually become lost to sight. Like distant islands appearing further and farther apart on a slowly receding coastline. Think about the cosmic microwave background radiation, that faint afterglow of the Big Bang, still detectable today as a uniform glow permeating all space. It is like an echo from the universe's infancy, carrying information about its earliest moments. But this background is itself affected by the accelerating expansion. As space expands, the wavelengths of this microwave light are stretched out, a phenomenon known as cosmological redshift. Over time, these waves will become increasingly longer and fainter, until they reach a point where they essentially disappear from view, becoming lost to our instruments and unable to be detected. It is not that the radiation dies. It simply fades into an invisible realm, swallowed by the ever-growing darkness. And what is left then? You will find yourself within your local group, the Milky Way, Andromeda, Triangulum, and countless smaller galaxies bound together by gravity, drifting alone in an almost unimaginable, silent, dark void. This is not a sudden, violent event. It is a gradual process, a serene descent into eternal isolation, an echo of what is to come for all the universes beyond our own. The expansion continues without pause, relentlessly pushing each structure, each galaxy, each star system, each planet further and further from any potential neighbor. It is a journey not of speed or distance, but one of increasing solitude, a slow, inevitable separation from everything you once knew. Consider the timescale involved, truly staggering. We are talking about epochs far exceeding the lifespan of our sun, far beyond the estimated age of the universe itself. The scales are so vast that they are difficult to conceptualize, but perhaps by envisioning it as a coastline receding into an endless ocean, you can begin to grasp the profound implications. The galaxies closest to us will eventually move so far away that their light becomes too faint to detect. Their signals, the stars within them, the supernova that punctuate cosmic history, will diminish and fade until they are lost to our sight, becoming mere ghosts in the ever-darkening universe. And as this isolation deepens, something else will also change: the very nature of time itself. Scientists suspect that over such immense timescales, the laws of physics as we currently understand them may begin to fray at the edges, altered by the expansion and the extreme conditions. The fundamental constants, the values governing gravity, electromagnetism, and other forces, might not remain perfectly fixed, leading to unpredictable changes in how matter interacts with itself. This is not a prediction of imminent chaos. Rather, it is an acknowledgement that our current models are incomplete and may break down under these extreme conditions. The prevailing theory suggests what has become known as the heat death of the universe, a state where all energy is evenly distributed, all temperature differences have vanished, and no further processes can occur. This does not imply annihilation. It implies a cessation of structured activity, an ultimate equilibrium reached through endless expansion and dispersal. The Milky Way, once a vibrant spiral galaxy brimming with stars and nebulae, will eventually become just one faint, distant speck in an unimaginable sea of darkness. A slow fading echo of what was. It is important to remember that this journey is not necessarily a bad thing. There is no destructive force at play here, only the inevitable consequence of an expanding universe. It is a state of profound and absolute tranquility, an eternal night filled with nothing but cold emptiness. The stars themselves will eventually die out as their fuel runs dry, leaving behind only remnants, black holes, neutron stars, and the silent ghosts of once burning suns. And even these remnants will eventually decay in the face of Hawking radiation, the theoretical emission of particles from black holes over incredibly long periods. The universe in this distant future will be a place of silence like no other. The echoes of creation, the faint whispers of the Big Bang, will have been lost completely. You remain within a bubble of space and time, so utterly isolated that nothing ever enters or leaves, and nothing ever changes. A small corner of existence, existing entirely alone. The concept is both humbling and strangely comforting, a testament to the beauty and inevitability of cosmic processes. It is a picture of ultimate quietude, a final state of being where the universe has exhausted its potential for interaction. Not an end marked by destruction, but one defined by the absence of everything that once was. It is a profound meditation on scale and perspective, a reminder that our own existence is transient within the grand scheme of cosmic time, and that even the most vibrant and complex civilizations will eventually fade into the unending darkness. The journey to this distant future is not one of speed or drama. It is a slow, steady drift toward an eternal embrace with the void, a peaceful, silent surrender to the ultimate fate of everything. Close your eyes for a moment, consider that gentle dissolution, and allow yourself to sink into stillness alongside this unfolding cosmic narrative. In the end, all that remains is the silent dark, a peaceful rest under the embers of a sleeping cosmos. As we drift further into the silence of curved space-time, the boundaries of what we can see begin to fade. In the cosmic night, we are all part of the edge of forever. Sleep now among the stars. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.